bright stars within it would be visible. Between the two cores, you'd see chaos. Stars from both galaxies mixed together, creating a complex, turbulent structure. Bright blue regions of star formation would dot the sky, glowing clouds where gas clouds have collided and ignited into new stars. And threading through everything would be dark lanes of dust, silhouetted against the background glow. But here's the remarkable thing. If you were standing on Earth at this moment, assuming Earth is still habitable, which it almost certainly isn't, you probably wouldn't notice anything unusual in your daily life. The sun would still rise and set. The seasons would still change if there were seasons. Life, if any existed, would continue. That's because even though the galaxies are colliding, the distances between individual stars are still enormous. The nearest stars from Andromeda might be many light-years away. There's no immediate danger of a collision with another star, no radiation surge, no gravitational disruption of Earth's orbit, just a slowly changing night sky. However, the galaxy as a whole is beginning to feel the effects. The Sun's orbit around the galactic center, which has been stable for billions of years, is now changing. Andromeda's gravity is pulling on everything in the Milky Way, and the result is that stellar orbits are becoming more chaotic. Some stars are being pulled toward Andromeda. Others are being flung outward, away from both galaxies. And some, including possibly the Sun, are having their orbits scrambled, sent into new paths that are more elliptical, more tilted, or more erratic than before. This orbital scrambling is one of the main effects of a galaxy merger. Before the collision, most stars in a spiral galaxy follow fairly circular orbits around the galactic center, all moving in roughly the same plane. This organized motion is what creates and maintains the spiral structure. But when you add the gravitational influence of another galaxy, that organization breaks down. Stars get kicked into new orbits that are more random, more three-dimensional. The gas clouds between the stars are affected even more dramatically. Unlike stars, which are basically point masses moving through space, gas clouds are extended structures that can collide with each other. When gas clouds from the Milky Way collide with gas clouds from Andromeda, they crash together at relative velocities of hundreds of thousands of miles per hour. The kinetic energy of this collision gets converted into heat. The gas heats up to millions of degrees, glowing in X-rays and ultraviolet light. But something else happens too. The collision compresses the gas. And when gas gets compressed, it can collapse under its own gravity if it reaches high enough density. This collapse forms new stars, lots of them. This is the starburst we mentioned earlier, and it's one of the most dramatic effects of the collision. Over the next few 100 million years, millions upon millions of new stars will form in the regions where gas clouds collide. These newborn stars are massive and hot, tens or hundreds of times the mass of the Sun. They burn through their fuel incredibly quickly, living only a few million years before exploding as supernovae. So the galaxy merger triggers not just star formation, but also a dramatic increase in the supernova rate. Now, supernovae are powerful events. A single supernova can briefly outshine its entire galaxy, releasing as much energy in a few weeks as the Sun will emit over its entire 10 billion-year lifetime. And supernovae don't just produce light, they produce high-energy radiation, cosmic rays, energetic particles traveling at nearly the speed of light. If you're anywhere near a supernova when it explodes, within maybe 100 light-years or so, the radiation can be dangerous. It could strip away a planet's ozone layer, exposing the surface to harmful ultraviolet light. It could cause mutations in any life that exists. It could potentially trigger mass extinctions. During the starburst phase of the merger, the supernova rate increases by orders of magnitude. Instead of 1 or 2 supernovae per century, which is typical for a normal galaxy, you might have dozens or hundreds per century. Any planets in the wrong place at the wrong time could be bathed in radiation. This is another reason why life during the merger would be challenging, even if your planet's orbit remains stable. Let's jump forward in time now. We're now roughly 4.5 billion years from today. The galaxies have been overlapping for about 500 million years. The two galactic cores, the dense central regions containing most of the mass, are approaching each other for the first time. This is called the first core passage, and it's one of the most dramatic moments of the entire merger. The galactic cores are incredibly dense regions. The density of stars near the Milky Way's center is thousands of times higher than the density out here in our neighborhood. And when two galactic centers pass through each other, you temporarily have double the density. This creates opportunities for close encounters between stars. While direct collisions are still rare, stars can pass close enough to each other that their gravitational influence becomes significant. A star might have its orbit drastically altered by a close pass with another star, or if a star has planets, those planets might be disturbed or even stripped away by the gravity of a passing star. For our solar system, this is one of the most dangerous moments of the entire merger. If we're unlucky enough to be near the core during this passage, there's a small but real chance that a close encounter with another star could disrupt the orbits of the planets. Jupiter might be knocked into a different orbit. Earth, if it still exists, might be pushed closer to the Sun or farther away. In a worst-case scenario, planets could be ejected from the solar system entirely, sent wandering into interstellar space as rogue planets. But let's put that risk in perspective. Even in the dense environment near the galactic core, the chances of any individual star having a disruptive close encounter are pretty low. Most stars, including probably the Sun, will pass through this period without any direct interactions. The distances are still just too large. What's more likely to affect us is the indirect effects. The gravitational chaos of the merger will send ripples through the entire galaxy. These ripples can disturb the orbits of everything, not just stars, but also gas clouds and the dark matter that makes up most of the galaxy's mass. And these disturbances can trigger events far from the core. The density of the galactic core during this passage would be something to behold. If you could somehow watch from a safe distance, you'd see two bright, compact regions of stars approaching each other, each surrounded by a haze of gas and dust. As they pass through each other, the gravitational interactions would cause the gas to heat up dramatically, glowing in X-rays and ultraviolet light. Some of this gas would fall toward the supermassive black holes, feeding them and causing them to become temporarily more active. When a black hole feeds, it doesn't just swallow material silently. The infalling matter forms an accretion disk, a swirling disk of superheated gas orbiting the black hole at nearly the speed of light. This disk can outshine the entire galaxy, radiating enormous amounts of energy. If both black holes become active during the core passage, the centers of both galaxies would light up brilliantly. From a distance, you'd see two intensely bright points of light, like cosmic headlights rushing toward each other. This would be a spectacular sight for any observers in nearby galaxies. Now, let's talk about what happens to the supermassive black holes. This is one of the most fascinating parts of the merger, and it's something astronomers are intensely interested in. When the two galactic cores pass through each other for the first time, the black holes don't immediately merge. They're still separated by thousands of light years, maybe more. But as the galaxies swing back together for subsequent passages, the black holes get closer and closer. Eventually, after multiple passages over hundreds of millions of years, they end up orbiting each other. Two supermassive black holes, one weighing 4 million solar masses and the other weighing perhaps 100 million to 200 million solar masses, circling around their common center of mass. This is called a binary black hole system, and it's an incredibly powerful source of gravitational waves. Gravitational waves are ripples in space-time itself, created by accelerating massive objects. They were predicted by Einstein over a century ago, but weren't directly detected until 2015. Since then, we've detected gravitational waves from dozens of black hole mergers, but all of them involved stellar mass black holes, the kind that form when massive stars die. We haven't yet detected the merger of two supermassive black holes, but we know it must happen during galaxy mergers. When Sagittarius A star and Andromeda's black hole orbit each other closely, they'll emit gravitational waves at a low frequency, lower than what our current detectors can sense. Future space-based detectors should be able to detect these waves. Any sufficiently advanced civilization in the local group would be able to observe this event in gravitational waves, watching as the two black holes spiral together. The orbital period gets shorter and shorter as the black holes lose energy to gravitational waves. They might orbit each other for millions of years, but eventually they get close enough that the orbital period drops to hours, then minutes, then seconds. And then, finally, they merge. The merger itself happens incredibly quickly. Two black holes orbiting each other at a significant fraction of the speed of light suddenly combine into a single larger black hole. The new black hole will weigh roughly 104 million to 204 million solar masses, the sum of the two original black holes. In the process, some mass gets converted directly into energy in the form of gravitational waves. The amount of energy released is staggering. In just a few seconds, the merger releases more energy than all the stars in both galaxies combined will emit over millions of years. It's the most powerful event in the universe, except for the Big Bang itself. But here's the thing, that energy is emitted as gravitational waves, not light. So unless you have a gravitational wave detector, you won't see anything. The night sky won't suddenly light up. There won't be a visible explosion. The black holes will quietly merge, shaking the fabric of space-time but not creating any visible display. After the merger, the new black hole will likely receive a kick, a recoil effect from the asymmetric emission of gravitational waves. This kick can be powerful enough to send the black hole moving through the galaxy at hundreds or even thousands of miles per second. Eventually, it will settle down at the center of the new merged galaxy, but for a while, it might wander. This wandering supermassive black hole is another potential hazard. The chances of it coming anywhere near any individual star system are vanishingly small, but if it did pass close to a star, it would be catastrophic. The black hole's immense gravity would tear the star apart, creating a spectacular tidal disruption event that would briefly outshine the entire galaxy. The kick velocity depends on the spins and masses of the two black holes. If they're spinning in the same direction and their spins are aligned, the kick is relatively small. If they're spinning in opposite directions or at odd angles, the kick can be much larger. Computer simulations suggest kicks of up to several thousand miles per second are possible. A black hole moving at these speeds would take millions of years to slow down and settle at the galactic center. During this time, it would plow through the galaxy, occasionally encountering stars and gas clouds. Any star that came too close would be captured or disrupted, adding to the black hole's mass. Let's get into the details of what happens to individual stellar systems during the merger. We've said that direct collisions between stars are rare, but close encounters can still have dramatic effects. Imagine two stars passing within a few light weeks of each other. That's close by cosmic standards, but still far enough that the stars don't physically touch. As they approach, their gravitational fields interact. Each star tugs on the other, altering its trajectory. It's similar to what happens when two billiard balls collide, except the stars don't physically touch. They interact through gravity alone, and the encounter happens over months or years as the stars approach, reach their closest point, and then recede. The outcome of a stellar encounter depends on several factors: how close the stars get, how fast they're moving relative to each other, and their masses. If two stars pass within a few light weeks of each other while moving at typical galactic velocities, which are hundreds of thousands of miles per hour, they'll exchange some energy and momentum. One star might be sped up slightly while the other is slowed down. Their directions of motion will change, bending their paths through space. This is called gravitational deflection, and it's the primary mechanism by which stars' orbits get randomized during a galaxy merger. Now, if the stars happen to be moving slowly relative to each other and they pass very close, something more interesting can happen. They might temporarily become gravitationally bound to each other, forming a binary star system. This would be a loose binary, with the two stars orbiting each other at a distance of light months or light years. But it would be stable over millions of years. However, if a third star comes along and interacts with this binary, the system becomes unstable. Three-body gravitational interactions are chaotic and unpredictable. The most common outcome is that one star gets ejected at high speed, becoming what's called a hypervelocity star, while the other two form a tighter binary. This process, called binary hardening through three-body interactions, is one way that close binary star systems form. Hypervelocity stars are fascinating objects. These are stars moving so fast that they can escape the galaxy's gravity entirely. They've been accelerated to speeds of hundreds or even thousands of miles per second, fast enough to reach escape velocity. We've detected several hypervelocity stars in the Milky Way, and they're thought to be created by interactions with the supermassive black hole at the galactic center, or by binary interactions in dense stellar environments. During the merger, the creation of hypervelocity stars will increase dramatically. Close encounters between stars will be more common, especially during the core passages. Some of these encounters will result in stars being flung out of the galaxy at enormous speeds. These stars, along with any planets they might have, will become intergalactic travelers, leaving the merged galaxy entirely and heading out into the void between galaxies. There's also the question of what happens to existing binary star systems during the merger. Many stars are already in binary or multiple star systems, orbiting each other in stable configurations. During a close encounter with a third star, these systems can be disrupted. The intruder star might pull one component away from the binary, breaking it apart. Or it might join the system, creating a triple star system. Triple star systems are less stable than binaries and often undergo complex gravitational interactions that eventually result in one star being ejected. Now, what about planetary systems? If a star has planets, what happens to them during the merger? In most cases, probably nothing. The planets are bound to their star much more strongly than the star is bound to the galaxy. It would take a very close encounter with another star to disrupt a planetary system. But close encounters do happen, especially during the core passages. Let's imagine a scenario where another star passes within about half a light year of the Sun. That's roughly 3 trillion miles. Far enough that there's no danger of collision, but close enough that gravitational effects become significant. The outer planets, especially those on the outskirts of the solar system or any objects in the Oort cloud, might be affected. A passing star's gravity could perturb their orbits, making them more elliptical or even ejecting them entirely from the solar system. The inner planets, if they still exist at this point, would probably be safe. They're closer to the Sun and more tightly bound. It would take a much closer pass to disrupt their orbits. But there's another effect to consider. The Oort cloud, that vast spherical shell of comets surrounding the solar system at a distance of roughly 1 light year, is only very loosely bound to the Sun. A passing star could easily disturb the Oort cloud, sending comets into the inner solar system. This could trigger a period of increased comet impacts on the planets. We've actually seen this happen in our own history. There's some evidence that close encounters with other stars in the past have disturbed the Oort cloud and triggered comet showers that resulted in impact events on Earth. During the merger, these encounters would be more common. The merger might also create planetary systems with very different architectures from what we're used to. During close stellar encounters, while complete disruption is rare, subtle gravitational perturbations can occur. A planet on an initially circular orbit might be nudged into a more elliptical orbit. Multiple planets in a system might have their orbital resonances disrupted, leading to instabilities that play out over millions of years. Some planetary systems might even capture planets from other systems during close encounters. Imagine two stars passing within half a light year of each other. A planet on a wide orbit around one star might be pulled away by the gravity of the other star, switching allegiance mid-flight. This would create planetary systems with a mix of planets from different origins, possibly with very different compositions and histories. During the merger, the chaotic gravitational environment will likely create many rogue planets. A close encounter between two stars might eject planets from one or both systems. These planets become interstellar wanderers, drifting through the galaxy on their own. Some estimates suggest there might already be as many rogue planets as there are stars, and the merger could substantially increase this population. For any life on a rogue planet, assuming life could exist in such a cold, dark environment, the merger would be an interesting time. The planet would pass through regions of increased stellar density, occasionally coming close to stars or other planets. There might even be rare occasions when a rogue planet gets captured by a new star, joining a new planetary system entirely different from the one it was born in. Let's also think about what happens in different regions of the galaxies during the merger. The experience of a star system will depend heavily on where it's located. Stars in the central regions, near the galactic cores, will experience the most dramatic effect. The density is highest there, so close encounters are most likely. The gravitational chaos is most intense. The starburst is most active. The supernova rate is highest. A planetary system in the central regions would face significant hazards. Close encounters with other stars could disrupt planetary orbits. Supernova explosions could bathe the system in harmful radiation. The intense star formation would create a bright, energetic environment with lots of ultraviolet light and X-rays. Stars in the outer regions, far from the cores, will have a much calmer experience. The density is lower, so close encounters are less likely. The gravitational effects are more subtle. The starburst is less intense. A planetary system in the outer regions might barely notice the merger is happening, at least in terms of immediate local effects. The main change would be the night sky, which would gradually become more complex and chaotic as the galaxies interpenetrate. Stars in the disk, the flat part of the galaxy between the core and the outer halo, will have an intermediate experience. Some disk regions will experience intense star formation as gas clouds collide. Other disk regions, away from the main collision zones, will be relatively calm. The fate of any individual star system is somewhat random, depending on the details of its orbit and the chance encounters it has with other stars. But statistically, most stars will survive the merger without any catastrophic encounters. Most planetary systems will survive with their planets still in roughly their original orbits. The main change for most star systems will be the new galactic environment they find themselves in after the merger. Instead of a neat spiral galaxy with organized rotation, they'll be in an elliptical galaxy with random stellar motions. Instead of being part of a thin disk, they might be part of a thick spheroid. Instead of orbiting in a relatively uncrowded region, they might find themselves in a denser or sparser region than before. After the first core passage, the two galaxies don't just stick together. They're moving too fast for that. Instead, they swing past each other, pulled apart by their own momentum, and then gradually slow down and swing back together for a second pass. This happens because they haven't lost enough energy yet. During the first passage, some energy is transferred between the stars through gravitational interactions. Some stars are sped up, others are slowed down. This energy exchange acts like friction, gradually removing energy from the orbital motion of the two galaxies. But it's not enough to make them merge immediately. So the galaxies separate again, their cores moving apart to a distance of hundreds of thousands of light years. Then gravity pulls them back together for a second passage, then a third, then a fourth. Each time, they lose more energy. Each time, they don't separate quite as far. Eventually, after maybe 5 or 6 passages, over 1 billion years or so, they lose enough energy that they can't separate anymore. The cores merge permanently, forming a single galactic core. During all of this, the structure of both galaxies is being completely destroyed. The neat spiral arms that characterized both the Milky Way and Andromeda are gone, torn apart by tidal forces and gravitational interactions. The organized rotation that maintained those spiral arms has been replaced by chaotic, random motions. Stars that were moving in orderly circular orbits are now moving in elliptical orbits with random orientations. The result is that the merged galaxy no longer looks like a spiral. It looks like what astronomers call an elliptical galaxy. Elliptical galaxies are shaped like elongated spheres or footballs. They don't have spiral arms or disks. They don't have much gas left, because most of it was used up in the starburst. They're dominated by old red stars moving in random orbits. This is the final product of the merger. A giant elliptical galaxy, probably about 200,000 to 300,000 light-years across, containing the combined stars from both the Milky Way and Andromeda. Astronomers have already given this future galaxy a name: Milkomeda, or sometimes Milkdromeda. Milkomeda will be one of the largest galaxies in the local group. It will contain roughly 1.2 trillion stars, maybe more, and it will look completely different from either of its parent galaxies. No spiral arms, no disk, just a vast, roughly spherical collection of stars. Let's talk more about what Milkomeda will actually look like and how it will function as a galaxy. From the outside, if you could view Milkomeda from another galaxy, you'd see a bright, roughly elliptical blob of light. The core would be very bright, containing a dense concentration of stars and the merged supermassive black hole. Moving outward from the core, the brightness would gradually fade as the stellar density decreases. The color of Milkomeda would be different from its parent galaxies. Spiral galaxies like the Milky Way and Andromeda have a mix of blue regions where young hot stars are forming and redder regions where older, cooler stars dominate. Elliptical galaxies tend to be redder overall because they've used up most of their gas in starbursts and have little ongoing star formation. By the time Milkomeda forms, perhaps 6 or 7 billion years from now, the starburst will be mostly over. The gas will have been consumed or blown away by supernova winds. What remains are the stars that formed during the merger, plus all the stars that existed before. The young massive stars from the starburst will have died, many of them exploding as supernovae. What remains from the starburst are the longer-lived stars, those with masses similar to the Sun or smaller. These stars will still be shining billions of years after the merger, gradually aging and cooling. Most of the stars in Milkomeda will be old, red stars. The original stars from the Milky Way and Andromeda will be even older than they are today, many of them red giants or white dwarfs. The merger-era stars will be middle-aged, similar to what the Sun is today. And there will be very few young blue stars because there's little gas left to form new stars. This gives Milkomeda its reddish color, the characteristic color of elliptical galaxies. The structure of Milkomeda will be very different from a spiral galaxy. Instead of a thin disk with spiral arms, Milkomeda will have a thick, three-dimensional distribution of stars. Stars will move in all directions, on orbits with random orientations and eccentricities. Some stars will have nearly circular orbits. Others will have highly elliptical orbits that take them from the core to the outer regions and back. Some will orbit in one plane, others in perpendicular planes. There's no overall rotation like there is in a spiral galaxy. This random motion is a result of the gravitational interactions during the merger. All that scrambling and kicking of stellar orbits results in a system where orbits are thoroughly mixed. At the very center of Milkomeda will sit the merged supermassive black hole, weighing perhaps 100 million to 200 million solar masses. Surrounding the black hole will be a dense stellar core, a region where stars are packed thousands or even tens of thousands of times more densely than they are in our current neighborhood. In this core region, the night sky from any planet would be spectacular. Thousands of stars would be visible to the naked eye. The brighter stars would cast noticeable shadows. The combined light from all these stars would create a permanent twilight, even during the night. True darkness would be almost impossible to find. But this dense environment also comes with hazards. Close encounters between stars would be more common in the core. While still rare in absolute terms, the frequency would be much higher than in the outskirts. Any planetary systems in the core would face increased risk of disruption over time. The supernova rate would also be higher in the core, at least for a while after the merger. The starburst creates many massive stars that live fast and die young. Even after the starburst ends, these stars will continue exploding for millions of years. The core regions would be bathed in supernova radiation more frequently than the outskirts. Moving outward from the core, the density gradually decreases. In the middle regions of Milkomeda, perhaps 50,000 to 100,000 light-years from the center, the stellar density would be more comparable to what we experience today. Stars would be separated by light-years, close encounters would be rare, and the night sky would look more like what we're used to. Farther out, in the outer halo of Milkomeda, perhaps 200,000 light-years or more from the center, the stellar density would be very low. Stars would be separated by tens of light-years. The night sky would be dark, with relatively few stars visible. The galactic core would appear as a bright, fuzzy ball of light in the distance. Throughout Milkomeda, there would also be globular clusters. These are dense, roughly spherical collections of stars, typically containing hundreds of thousands or millions of stars in a volume just tens of light-years across. Both the Milky Way and Andromeda currently have populations of globular clusters orbiting them. After the merger, these globular clusters will still exist, now orbiting Milkomeda. Globular clusters are interesting because they contain some of the oldest stars in the universe. They formed early in the history of their parent galaxies, often more than 10 billion years ago. The stars in globular clusters are metal-poor, meaning they contain very little of the heavier elements beyond hydrogen and helium. This is because they formed before generations of stars had enriched the interstellar medium with heavier elements through supernova explosions. During the merger, some globular clusters might be disrupted by gravitational interactions. Others might survive intact. And new globular clusters might form during the merger from gas clouds that collapse under unusual conditions. Milkomeda will also contain remnants of the tidal tails. Remember those long streams of stars pulled out of each galaxy during the approach? Some of those stars will eventually fall back into Milkomeda, accreted over billions of years. Others will remain in the intergalactic space around Milkomeda. forming diffuse streams and shells of stars orbiting at great distances. These stellar streams are actually observable in elliptical galaxies today. Astronomers use them as fossil records, tracers of past merger events. By studying the positions and velocities of stars in these streams, we can reconstruct the history of the mergers that created the elliptical galaxy. Future astronomers living in Milky billions of years from now could do the same. By studying stellar streams around their galaxy, they could piece together the history of the Milky Way-Andromeda merger, figuring out when it happened, how the galaxies approached each other, and what the resulting dynamics were. Now, let's talk more about dark matter, because we haven't discussed it in depth yet, and it plays a crucial role in the merger. We've mentioned that galaxies are embedded in halos of dark matter, but what exactly is dark matter, and how does it behave during the merger? Dark matter is one of the biggest mysteries in modern physics. We know it exists because we can see its gravitational effects, but we don't know what it's made of. It doesn't emit, absorb, or reflect light. It doesn't interact with electromagnetic radiation at all. The only way we know it's there is through gravity. Galaxies rotate faster than they should based on the visible matter alone. If you calculate the rotation curve of a galaxy, the speed at which stars orbit at different distances from the center, and you base that calculation only on the visible mass, the stars and gas, you find that the outer stars should be moving much slower than they actually are. They're moving so fast that they should fly off into space, not remain in orbit. The only explanation is that there's additional mass we can't see. This invisible mass provides the extra gravity needed to keep the outer stars in their orbits. That invisible mass is dark matter. Galaxy clusters show the same effect. The galaxies in a cluster are moving so fast that the cluster should fly apart unless there's much more mass than we can see. Again, dark matter provides the solution. Gravitational lensing provides even more direct evidence. When light from a distant galaxy passes near a massive object like a galaxy cluster, the gravity of the massive object bends the light, acting like a lens. By measuring how much the light is bent, we can calculate how much mass is doing the bending. And consistently, we find much more mass than we can account for with visible matter. All of this evidence points to dark matter, making up roughly 85% of the total matter in the universe. Only 15% is normal matter, the atoms that make up stars, planets, and us. But what is dark matter made of? That's the mystery. It's not normal atoms, we know that. If it were, it would interact with light and we'd be able to see it. The leading hypothesis is that dark matter consists of some exotic particle that we haven't discovered yet. Maybe WIMPs, weakly interacting massive particles. Maybe axions. Maybe something else entirely. Physicists have been searching for dark matter particles for decades, building sensitive detectors deep underground to shield them from cosmic rays, hoping to catch a dark matter particle interacting with normal matter. So far, no confirmed detection. But whatever dark matter is made of, we know it interacts through gravity, and that's all that matters for the galaxy merger. During the merger, the dark matter halos of the Milky Way and Andromeda will merge just like the visible parts of the galaxies. But the dark matter behaves differently from the stars and gas. Stars are discrete objects moving on ballistic trajectories. They respond to gravity but don't collide with each other. Gas clouds can collide. When gas clouds hit each other, they can lose energy through radiation, cooling down, and potentially collapsing to form stars. Dark matter is even more collisionless than stars. Dark matter particles pass right through each other without interacting. They don't collide, they don't lose energy through radiation. They just respond to gravity. This means that when the dark matter halos merge, they interpenetrate freely. Dark matter from the Milky Way passes through dark matter from Andromeda without any collisions or interactions beyond gravity. Computer simulations of galaxy mergers need to track the dark matter separately from the stars and gas because it behaves differently. The simulations show that after the merger, Milkomeda will be embedded in a roughly spherical halo of dark matter, extending perhaps 600,000 to 1 million light-years from the center. This dark matter halo will contain most of Milkomeda's mass, perhaps 85 to 90% of the total. The stars, gas, and everything we can see will account for only 10 to 15%. The dark matter determines the overall gravitational potential well in which the visible galaxy sits. It's like the scaffolding, the underlying structure. The visible matter falls into this gravitational well and settles into the distribution we observe. Understanding how dark matter behaves during mergers is crucial for understanding galaxy evolution. And astronomers can test their models of dark matter by comparing simulations to observations of real galaxy mergers. If dark matter behaves the way we think it does, simulations should match observations. And indeed, they do, at least to a good approximation. This gives us confidence that our understanding of dark matter, while incomplete, is on the right track. Now, let's ask a more philosophical question. If intelligent life still exists somewhere in the solar system, or in the galaxy generally during this time, what would it be like to live through the merger? First, remember that this entire process takes billions of years. No individual organism, not even an individual civilization in any recognizable form, would experience the whole thing. You'd need a continuous chain of civilizations, each one building on the knowledge of the previous, to maintain awareness of what's happening over such vast timescales. Or you'd need a civilization that achieves some form of extreme longevity, either biological or technological. Maybe they upload their minds into computers. Maybe they achieve functional immortality through advanced medicine. Maybe they become some form of post-biological intelligence. But let's imagine such a civilization exists. What would they observe? In the early stages, millions of years before first contact, they'd see Andromeda growing larger in the sky. Their astronomers would be able to predict the collision with increasing accuracy as observations accumulate. They'd map the approaching galaxy in detail, identify its structure, locate its supermassive black hole, estimate the timing of first contact. They'd have centuries or millennia of advanced warning, perhaps longer. This would give them time to prepare, to move populations if necessary, to build infrastructure that could withstand the changes. A sufficiently advanced spacefaring civilization could evacuate entire regions of the galaxy that were expected to be particularly affected. They could relocate populations to safer areas, perhaps the outer halo where stellar density is low and encounters are unlikely. They could build space habitats that aren't tied to any particular star, mobile habitats that can move between star systems as needed. This would give them flexibility to avoid dangerous regions and seek out opportunities. As the galaxies draw closer, they'd see the tidal distortions begin. Long streams of stars pulled from each galaxy would become visible. The rate of supernova explosions in both galaxies would increase as the starburst began. The night sky would gradually brighten and become more chaotic. They might even detect the gravitational waves from the merging supermassive black holes if they had advanced enough technology. Gravitational wave astronomy would give them a completely different view of the merger, revealing the dynamics of the supermassive black holes as they spiral together. During the actual core passages, assuming they had telescopes and sensors scattered throughout the region, they'd observe vast structures in motion, spiral arms being torn apart, gas clouds colliding and igniting into new star-forming regions, the galactic cores approaching each other, passing through, separating, and coming back together. It would be a spectacle on an unimaginable scale, playing out over millions of years but observable in its entirety through records, predictions, and multi-generational observation programs. But what about the dangers? Would a civilization living through the merger be in peril? The answer depends on where they are and what resources they have. If they're confined to a single planet, they're vulnerable. An increased rate of supernova explosions could bathe their planet in harmful radiation. A close encounter with another star could disrupt their planet's orbit or trigger comet impacts. Climate changes from varying stellar radiation could make their world uninhabitable. But if they're a spacefaring civilization with the ability to move between star systems or build habitats in space, they can avoid most of these dangers. They could simply relocate away from dangerous regions and move to safer areas. A civilization with true interstellar capability wouldn't be tied to any one location. They could ride out the merger by staying in the safest regions, moving as needed, and avoiding the most chaotic areas. In fact, a sufficiently advanced civilization might even benefit from the merger. The starburst creates millions of young, hot stars that could serve as energy sources. The gravitational chaos might scatter valuable resources, such as metal-rich asteroids or comets, throughout the galaxy, making them more accessible. New star systems are forming constantly during the starburst, offering opportunities for colonization. From this perspective, the merger isn't necessarily a disaster. It's a transformation, a change from one type of galaxy to another. Whether that's good or bad depends entirely on your perspective and capabilities. A primitive civilization confined to one planet would see the merger as an existential threat. An advanced spacefaring civilization would see it as a period of change, certainly, but not necessarily catastrophic. They might even view it as an opportunity, a chance to spread to new star systems, to harvest the energy of young hot stars, to explore the newly chaotic galactic environment. Let's also consider what happens even farther into the future, beyond the formation of Milkomeda. Milkomeda won't be the end of the story for our cosmic neighborhood. The local group contains other galaxies besides the Milky Way and Andromeda, and over time, these smaller galaxies will merge with Milkomeda too. The Triangulum galaxy, the third largest member of the local group, might merge with Milkomeda. The timing is uncertain because Triangulum's orbit is complex and its exact trajectory isn't perfectly known, but computer simulations suggest it could merge with Milkomeda perhaps 1 billion or 2 billion years after the Milky Way-Andromeda merger. When Triangulum merges, it will add perhaps 40 billion to 50 billion more stars to Milkomeda. The merger will trigger another, smaller starburst as Triangulum's gas collides with any remaining gas in Milkomeda. More spiral structure will be destroyed, further randomizing stellar orbits. There are also dozens of dwarf galaxies orbiting both the Milky Way and Andromeda. These small galaxies, containing millions or billions of stars, are slowly falling toward their parent galaxies due to dynamical friction. This is a process where a massive object moving through a background of less massive objects gradually loses energy and slows down. The dwarf galaxies will gradually spiral inward and eventually be absorbed by Milkomeda. Each merger will add stars to Milkomeda and slightly perturb the orbits of existing stars. But because the dwarf galaxies are so small compared to Milkomeda, these mergers won't dramatically alter the overall structure. Over tens of billions of years, all the galaxies in the local group will eventually merge into a single giant galaxy. This is the ultimate fate of our cosmic neighborhood. Gravitationally bound structures merge over time unless something prevents it. But there's something else happening on an even larger scale that will profoundly affect Milkomeda's future. The universe is expanding. Space itself is stretching, carrying galaxies away from each other. This expansion was discovered by Edwin Hubble in the 1920 seconds. He observed that distant galaxies show redshifts in their spectra, indicating they're moving away from us. And the farther away a galaxy is, the faster it's receding. This led to the realization that the universe itself is expanding. It's not that galaxies are moving through space, it's that space itself is growing, stretching, carrying galaxies along with it. And not only is the universe expanding, but in 1998, astronomers discovered that the expansion is accelerating. Distant supernovae appeared dimmer than expected, suggesting the universe is expanding faster now than it was in the past. This acceleration is driven by something called dark energy, an even more mysterious component of the universe than dark matter. Dark energy acts like a kind of anti-gravity on cosmic scales. It doesn't push galaxies apart directly. Instead, it causes space itself to expand faster. We don't know what dark energy is. We don't know why it exists. We just know it's there because we can see its effects on the expansion of the universe. Current observations suggest that dark energy makes up about 68% of the total energy content of the universe. Dark matter makes up about 27%. Normal matter, everything we can see, accounts for only about 5%. The universe is dominated by components we don't understand: dark matter and dark energy. What does this mean for Milkomeda? On scales smaller than a few tens of millions of light-years, dark energy doesn't matter much. Gravitationally bound structures like galaxies and galaxy groups aren't torn apart by the accelerating expansion. Gravity within these structures is strong enough to overcome the expansion, but on larger scales, the accelerating expansion dominates. Galaxies and galaxy clusters that aren't gravitationally bound to each other are being carried apart by the expansion, and as time goes on, they're receding faster and faster. Eventually, trillions of years from now, galaxies outside the local group will recede so far and so fast that light from them can no longer reach us. They'll disappear beyond the cosmic horizon, the boundary beyond which light can't catch up to us because space is expanding too fast. At that point, any astronomers living in Milkomeda will look out and see only their own galaxy and perhaps a few nearby companions that merged with it. No other galaxies visible anywhere. No evidence that the universe contains anything beyond their cosmic island. They might conclude, based on their observations, that the universe consists of just one galaxy and nothing else. They'd be wrong, of course. The rest of the universe would still exist, billions of galaxies in every direction, but it would be forever beyond their ability to observe. This has profound implications. Future civilizations will have a fundamentally different view of the universe than we do. They won't see the cosmic web of galaxies. They won't see the large-scale structure of the universe. They won't be able to study distant galaxies to learn about the universe's history and evolution. We're living in a special time, cosmologically speaking. The universe is old enough that we can study its history, look back at the cosmic microwave background radiation from the Big Bang, observe distant galaxies as they were billions of years ago. But the universe is young enough that we can still see this vast cosmic structure. The billions of galaxies, the clusters and superclusters, the cosmic web. Future civilizations won't have this advantage. They'll live in an older, emptier-looking universe. This isn't just philosophical speculation. It has practical implications for astronomy and cosmology. If we lived in Milkomeda 100 trillion years from now, we might not be able to discover many of the things we know today. We couldn't measure the expansion of the universe by observing distant galaxies because there wouldn't be any visible distant galaxies. We couldn't study galaxy evolution across cosmic time. We couldn't observe the cosmic microwave background because it would have redshifted to undetectable wavelengths. Our knowledge of the universe depends on the cosmic time at which we exist. We're fortunate to live when we do, at a time when the universe is observable and comprehensible. But returning to Milkomeda specifically, what will its long-term future be? Over trillions of years, star formation in Milkomeda will gradually cease. The gas will all be used up, converted into stars, or expelled from the galaxy by supernova winds. Without gas, no new stars can form. The massive stars will die first, living only millions of years. Then stars like the Sun will die, lasting billions of years. Eventually, even the smallest red dwarf stars will exhaust their fuel, though this takes trillions of years. As stars die, some will explode as supernovae, creating neutron stars or black holes. Others will shed their outer layers and become white dwarfs. Over time, the galaxy will come to consist mostly of stellar remnants, white dwarfs, neutron stars, and black holes. These remnants don't shine like stars. White dwarfs gradually cool, becoming black dwarfs, cold lumps of carbon and oxygen. Neutron stars cool and fade. Black holes don't emit anything except Hawking radiation, and for stellar mass black holes, that's negligibly small. Milkomeda will gradually darken. Instead of a bright galaxy full of shining stars, it will become a dark galaxy full of stellar corpses. The few remaining stars, the longest-lived red dwarfs, will be scattered through a sea of darkness. The night sky from any planet in such a galaxy would be nearly black. Almost no stars visible. The galactic core, instead of being a bright region, would be dark, just a concentration of black holes and white dwarfs. But even this isn't the end. Over even longer timescales, perhaps 10 to the 20th power years, stellar remnants will occasionally collide or get ejected from the galaxy through multi-body gravitational interactions. The galaxy will gradually evaporate, losing stars to intergalactic space, and the supermassive black hole at the center will grow. Occasionally, stars or stellar remnants will fall into it, adding to its mass. Over tens of billions of years, the central black hole might grow to billions of solar masses. Eventually, perhaps after 10 to the 100th power years, even black holes will evaporate through Hawking radiation. Stephen Hawking showed that black holes aren't completely black. They emit radiation due to quantum effects near the event horizon. For stellar mass black holes, this radiation is incredibly weak, negligible compared to any other process. But over timescales of 10 to the 100th power years, even supermassive black holes will slowly evaporate. When the last black hole evaporates, Milkomeda will consist of nothing but photons, neutrinos, and whatever fundamental particles are stable over these timescales. The galaxy will have effectively dissolved into radiation. But these timescales are so long that they're almost meaningless. 10 to the 100th power years is a 1 followed by 100 zeros. The current age of the universe is only about 14 billion years. 4 times 10 to the 10th power. The timescale for black hole evaporation is 90 powers of 10 longer than the current age of the universe. For all practical purposes, Milkomeda will exist as a dark galaxy of stellar remnants for an almost incomprehensibly long time. Far, far longer than it exists as a bright galaxy of shining stars. But during its bright phase, during the trillions of years when stars still shine, Milkomeda will be home to whatever life exists in our cosmic neighborhood. If intelligence survives, if civilization persists, it will be in Milkomeda. If life spreads to the stars, it will spread through Milkomeda. If consciousness explores the cosmos, it will explore Milkomeda. This merged galaxy will be the future home for everything that descends from life on Earth or life anywhere else in the Milky Way or Andromeda. Now, let's address one final question. Is there anything we can do about the merger? Could a sufficiently advanced civilization prevent it or mitigate its effects? The short answer is probably not, at least not with any technology we can currently imagine. The merger is driven by the gravitational attraction between two enormous galaxies. The forces involved are so vast that they dwarf anything we can conceive of controlling. To prevent the merger, you'd need to either increase the angular momentum of the system so that the galaxies go into stable orbits instead of colliding, or remove energy from the system somehow to make the galaxies repel each other. Both of these would require manipulating the motion of trillions of stars across millions of light years. The energy required would be immense, far beyond anything we can currently imagine harnessing. Even a Kardashev Type 3 civilization, a hypothetical civilization capable of harnessing the energy of an entire galaxy, would struggle with this task. You'd need to be able to redirect the motion of individual stars on a galaxy-wide scale, which would require technology so advanced that it's essentially indistinguishable from magic. But perhaps the question itself is misguided. Maybe the merger shouldn't be prevented. After all, galaxy mergers have been happening throughout cosmic history, and they've led to the formation of new galaxies, new stars, new planetary systems. The universe doesn't care about our categories or our labels. The Milky Way is just a collection of stars, gas, and dark matter bound together by gravity. Milkomeda will be the same, just a different collection arranged in a different structure. What matters isn't preserving the Milky Way as it is today. What matters is ensuring that whatever life exists in the future can thrive, regardless of what the galaxy looks like. And for that, the key isn't preventing the merger. The key is adaptability. A civilization that can move between star systems, that isn't tied to any one planet or star, can survive and thrive regardless of what happens on galactic scales. In fact, the merger might even be beneficial in some ways. It creates new stars, new opportunities, new regions to explore and colonize. It's a transformation, not an ending. As we come to the end of our journey through this collision, let's reflect on what we've learned. We started by understanding the two galaxies involved, the Milky Way, our home, a barred spiral galaxy containing hundreds of billions of stars, and Andromeda, larger and more massive, containing 1 trillion stars. We learned how astronomers discovered that these two galaxies are on a collision course using Doppler shift measurements and proper motion observations to determine their velocities and predict the timing. We walked through the merger itself, step by step, the gradual approach over billions of years, the formation of tidal tails as gravitational forces stretch both galaxies, the first contact as the outer edges overlap, the dramatic core passages as the dense central regions pass through each other, the starburst triggered by colliding gas clouds, the eventual merger of the supermassive black holes, and the final result, Milkomeda, a giant elliptical galaxy. We explored what this means for individual stars and planetary systems, how the Sun's orbit will be scrambled, how Earth will likely be uninhabitable long before the merger due to the Sun's evolution, how close encounters between stars, while rare, can disrupt planetary systems, and how the merger creates hypervelocity stars and rogue planets. We discussed the role of dark matter, the invisible scaffolding that makes up most of both galaxies and shapes how the merger proceeds. And we thought about what it might be like to live through the merger, the dangers and opportunities it presents, and how a sufficiently advanced civilization might adapt. Finally, we looked even farther into the future, to the ultimate fate of the local group, and the eventual isolation of Milkomeda, as the accelerating expansion of the universe carries distant galaxies beyond the cosmic horizon. The merger of the Milky Way and Andromeda is one of the most significant events in the future history of our cosmic neighborhood. It's a transformation on a scale so vast that it's difficult to comprehend, playing out over billions of years, reshaping hundreds of billions of stars, and creating a galaxy fundamentally different from either of its parents. And yet, for all its cosmic grandeur, it's also a story about the impermanence of the structures we see around us. The galaxies we observe today, including our own, are not eternal. They're temporary configurations of matter, held together by gravity, evolving and changing over cosmic timescales. The universe is dynamic, not static. It's evolving, transforming, constantly creating new structures while destroying old ones. And we're living in one moment of that vast cosmic story, able to look both backward at the universe's history and forward to its future. The collision with Andromeda is billions of years away. It won't affect anyone alive today or for countless generations to come, but knowing about it, understanding it, gives us a deeper appreciation for our place in the cosmos. We're not living in an unchanging universe. We're living in a universe that has a past and a future, where galaxies collide and merge, where stars are born and die, where structures form and dissolve. And that story, that epic tale of cosmic evolution spanning billions of years, is the story we've told tonight. The story of two galaxies on a collision course, of the transformation they'll undergo, of the new galaxy that will emerge. It's a story that reminds us how vast the universe is, how long the timescales are, and how small but precious our moment in that vast cosmic history really is. Thanks for staying with me through this long journey across space and time. The final hour of the collision may be billions of years away, but in cosmic terms, it's just around the corner. And when it finally arrives, when Andromeda's trillion stars meet the Milky Way's hundreds of billions, it will be one of the most spectacular transformations our corner of the universe has ever seen.